So, this video is just for you, Grace. Your mom said that you'd be really disappointed if you didn't get to do any chemistry for Friday. And she also wanted to hear my voice in your house, so say hi to Angela for me. All we did in class was talk about Arrhenius acids and Arrhenius bases. So we have this definition for an acid and a base. There are actually technically three different definitions for acids and bases, and we're really going to focus on what's important to us. So we might not even go over all those definitions in class. But the main definitions for acids and bases that are useful for us are acids are anything that produce hydrogen ion in solution. So we already talked about hydrochloric acid and how it ionizes to make hydrogen ion and chloride ion. And again, that's what makes it an acid to begin with. As long as I have this, I got one of those, right? If I produce hydrogen ion, it's an acid. We also talked about last chapter how that specifically works. How technically there's a water molecule that pulls on that hydrogen in that molecule, that hydrogen chloride molecule, and it essentially steals that hydrogen ion to make this hydronium. So depending on the context, sometimes you'll see this, sometimes you'll see the hydrogen ion specifically, but we know that hydrogen ion can't really float around free in solution. A water molecule is going to grab onto it to make this hydronium ion. So that is going to be an issue. We might have to go back and forth between those two things. But as long as a compound produces hydrogen ion or that hydronium in solution, it's definitely an acid. So the other example we had in class, that acetic acid, that vinegar, right, also produces hydrogen ion. And then you'd have that acetate ion as well. But again, as long as you see hydrogen ion, it's an acid. As long as that's produced in a solution, it's an acid, according to Arrhenius. So there are strong acids and weak acids. We do have to understand the difference. Right? And that came back to, we saw that my hydrochloric acid could be considered a strong acid, and that's because this reaction is reversible, but one direction is favored. 99+% of that compound is going to be ionized in solution. So we're going to have lots of ions to conduct electricity. That's a strong acid and also a strong electrolyte because of that. Right? So again, any of these reactions, they're all technically reversible. Right? Those products could recombine to form your reactants. But as long as you're favored in this direction towards the ions, it's a strong acid, it's a strong electrolyte. If you're favored in the other direction, it's actually going to be a weak acid or a weak electrolyte. For the acetic acid, more than 99% of it stays unionized, remains in that original form. Only it's less than 1% of it that turns into those ions, that ionizes. So that's what makes it a weak acid, right? So there are weak acids and there are strong acids. You do need to understand the difference. But otherwise, Arrhenius acids produce hydrogen ion in solution. Aqueous solutions of bases, we're going to have a couple different options. Excuse me. Arrhenius says that a base is anything that produces hydroxide in solution. So if I put sodium hydroxide in solution, it's going to dissociate, again, as opposed to ionizing, and it's going to have that hydrogen ion as a result. So if you see this, that hydroxide ion, as soon as you see hydroxide, you know you got a base. So it could be an ionic compound that contains that hydroxide. Maybe it's calcium hydroxide. But the only difference there, would be that now I have two hydroxides floating around in that solution as opposed to one, but it's still a base because of that hydroxide. But the other option, right, as long as whatever it is that I'm talking about reacts to produce hydroxide ion in solution, it's still going to be a base. So this ammonia compound doesn't have hydroxide in it, but it's still going to be considered a base because it'll react with water. It'll steal a hydrogen from water to become ammonium. But then the only thing left behind in that water is a hydroxide ion. Again, this is also a base because you get hydroxide in solution. Now the difference between strong and weak bases has to do with how much hydroxide ion you get in solution, obviously, but that sometimes could be misleading. Right? Sodium hydroxide is considered to be a strong base because you get lots of hydroxide ion in solution. You'd have a favoring of a reversible equilibrium towards those ions in solution. Right? All of that sodium hydroxide is going to dissolve, dissociate. You're going to have lots of hydroxide ion as a result. But that calcium hydroxide, it looks like it would make even more hydroxide ions than the sodium hydroxide, but because it's only weakly soluble, right? This is aqueous from last chapter. It's definitely going to dissolve. But calcium hydroxide is actually only very weakly soluble in solution. So even though you'd think it'd be more basic than the sodium hydroxide, it's less because the favoring in this equilibrium is towards the solid. Right? A little bit of ions will dissolve. We also talked about that last chapter. All ionic solids are slightly soluble, but if we talked about those precipitates, right, most of it came out of solution. Right, so the equilibrium is going to come into play again. This last example, right, ammonia is a weak base because 99+% of it is going to stay in that ammonia water form. Only a small amount, less than 1% of it, will react to make your hydroxide. So deciding whether it's a strong or weak base is a little bit harder than deciding if something's a strong or weak acid sometimes. So we'll figure that out later. That's all you're probably going to need. So we can stop here.